Welcome to the DPS session on Azure SQL Database Hyperscale, What's New and Beyond. My name is Denzil Ribeiro. I am a Principal Program Manager with the Azure Data team. Along with me, I have Balmukund Lakhani, who will also be co-presenting this session. I hope you guys are having a great DPS conference so far and hope you enjoy this session. As part of the agenda, we will look at the architecture, we'll look at what's new and what's recently released and what's upcoming in Hyperscale. We'll look at some troubleshooting and best practices as well, and some workloads that use Hyperscale currently. And last but not the least, happy to answer any questions on the topic. So first, let's look at the architecture. Hyperscale is designed as a cloud-native database. Prior to Hyperscale, we had Azure SQL database in the various tiers, but in Hyperscale, what is unique is separation of compute and storage. So all your initial connections, you get a database. So you connect to this initial database. That's called the compute. And the compute has, along with its local memory, also has a non-covering SSD cache. This is not a fully covering cache, rather a partial cache. It's intelligent in nature and caches the pages that are most used by your application that don't fit in memory. All your DML operations, whether inserts, updates, deletes, or data modifications, go to an externalized log service. So they're not committed locally, rather they're committed remotely. And this red path is the data path, if you will. And we'll see some changes in this log service that we've made in the upcoming slides. These changes are then propagated to kind of the storage layer. Everything from the page servers, only this compute blue box is what is customer exposed. Everything under this is to support the hyperscale architecture. So you have a covering set of page servers. So page servers are resilient by nature. It's a fully covering cache, which is based on local SSD. And then you have the durable media, which is Azure storage. So this, you have multiple blobs in Azure storage, and Azure storage can be configured in multiple ways that we'll see in a bit. So the data changes are propagated to these page servers, and page servers are resilient. Each of them have a replica for high availability. And then the log service itself also destages or archives log. This is based on your retention period. If you've the default retention is 7 days, so it'll keep 7 days of log. If you want to change it, you can. And then the green parts are really the read parts. So if your application reads a page that is not in memory, it requests for this page from the page servers. This log, the data changes that you've seen, is also applied to replicas. We have a set of HA replicas. The HA replicas are failover targets. You have up to 4 of them. They can also be used with application intent equal to read only, and read requests are load balanced across them. In addition to that, we also have a new concept that we'll dig into a little bit later called name replicas. Name replicas from a redo perspective, log is replayed on name replicas just like it is on HA replicas. If you note, different than availability groups, the primary replica doesn't directly talk to the secondary replicas. All the log flows via the log service to other components in the architecture, right? And then you have kind of backup restore via storage snapshots. So storage snapshots, mean it's a constant time backup and restore operation, because immaterial of the size of data, restoring from a snapshot is super quick, right? And then so next we'll look at the log service. In prior DPS conference last year, we had talked about the log service, and the architecture has changed a little bit. We now have a log service that has multiple replicas. So you have a primary replica and 2 secondary replicas. And this is done primarily for resiliency as well as for scalability. So when you commit a transaction, the application commits a transaction, it talks to compute, and then compute sends this commit to the primary replica of the log service, which then quorum commits to one of the other secondaries, right? And you can think of this like availability groups or business critical tier, with the log on local SSD here. The only difference being there's no data in this log replica. It's just log. So it's a very lightweight Hadron architecture, where you have this replica in a log accept mode. It doesn't do any redo or any function of redo. And then, you know, before in the prior architecture, the log commit actually went to premium storage or a remote SSD, and then the log service picked it up from there and moved on. Here, this replaces the need for that. So you have lower commit latency. You also have improved resiliency because you have multiple replicas. When log is transmitted or distributed to other parts of the system, like page servers, the page servers can read log from the secondary replicas, so it does help in scalability because there's read scale when distributing log to the other components into the system. And then log is destaged just like it would be in the prior architecture to long-term retention, which is Azure Standard Storage. And then the log service also distributes this log to compute replica, or the compute replicas request that log. And only redo is done of whatever pages are in its buffer pool or non-covering cache. We don't send all the log to compute replica, just the log it needs to service its read queries. And then we have some changes from a storage architecture perspective as well. And this is done primarily for the databases that existed in other tiers, such as business critical, so on and so forth. If you have an existing database on another tier, you could have files that are rather large, in the half terabyte to 1 terabyte range. And when those were migrated to Hyperscale, we now remove this 1:1 mapping between what you saw as a file on compute and what were the blobs on Azure storage. And the reason it was done that way was to remove any scalability limits that a single large blob would have on Azure storage. So what the compute sees as an NDF file, insist.database files, is now broken down into chunks. And each of these chunks, the page server still covers a 128 gig chunk, but the file itself, if it's a half a terabyte or 1 terabyte file on the compute, is broken into multiple chunks, which are then broken into 4 gig or small size blobs. So why small size blobs? So that each blob doesn't hit any of the per blob limits that exist, such as throttling, so that they can be read in parallel when we are seeding, for things like GODR seeding, for things like if page servers go down and they have to reseed from Azure storage. This enables, much faster seeding. It also enables performant migration from a business critical or general purpose, other tiers into Hyperscale. So that's the reason this storage was kind of re-architected. In terms of the page read lifecycle, this is not any different than before. You have blobs, a set of blobs sitting on Azure storage. If the first time the page server does come up, it does read these blobs and seeds its covering cache on local SSD. And this is where when you have multiple blobs, you can seed in parallel. And then these, if an application is reading a page from the primary database that it's connecting to, if the page is in its main memory, or if the page is on its non-covering cache, it really never leaves this compute. It doesn't have to do a remote read at all, right? If the page isn't there, then it has to do a get page from a set of page servers. Again, when it does a get page, if the page is caught up to that LSN that it requires, it just returns the page. If not, then it requests for the remainder of the log to apply to catch up that page and then returns, that page. So in terms of us having this intelligent cache called RBPX, prevents a lot of the page server writes, and so you get ultra fast latency. All the reads from local RBPX in the 1 millisecond range, remote reads are in the 2 to 5 millisecond range, and then the only time kind of you can get a little more latency is if this page is not caught up to the LSN that you required, because all the log replication is asynchronous. But this intelligent cache, we actually keep track of the hot pages being used and populate this cache. So as the application needs data, most of the data is actually serviced by the compute node. And this cache is proportional to the size of the slow. So the larger the tier you have, so for example, it's each core gets 5.1 gigs of memory, and the cache is 3 times the amount of the memory on that service objective. From a read scale scenario, we have multiple read scale options, if you will. We briefly had talked about in the first slide. So each compute primary has a high availability replica. These are failover targets, and you can have multiple of those. And if you specify application intent equal to read only, your application will reach there. You also have named replicas, which we'll cover in more detail, right? But for either of these are within a specific region. There is not a second copy of data. So it's one set of data which is serviced by all these replicas. Then you go cross region with geo-replication, and geo-replication has to have its own set of data, if you will. This is cross region. This is asynchronous in nature. And again, on the geo-replica, you can have its own HA replica or its named replicas. And then, like we said, all the log applied is asynchronous. So data's latency is always greater than 0. Within region, it's in the few millisecond range. If your application needs data as of the latest time frame up to the millisecond, then you need to read it from the primary. If not, you can scale out and you get a transactionally consistent point of view on read replica. The other thing is, any of these replicas, you can configure certain settings, such as with database scope configurations. So for example, you can set max degree of parallelism to be different on the replicas to service your read workloads than on the primary. So there are certain set of things that you can do, you can set for secondary being a different option than for primary. In this first demo, we'll look at fast scale up and how separation of compute and storage actually enables things like a fast scale up from one tier to another. Then we'll also look at auto scale down the line, but for now, fast scale up. So in this application, I have an application that will run a set of transactions, and on the left hand side, and on the right hand side, I have an application that actually makes connections to the database, runs a transaction. It connects every second, if you will, and you see that it'll print out the session and kind of that service tier, service objective. And it has transient fault handling and retry logic on a failed connection, and that's really to show you how long a failover takes. So looking at resources at this point of time, we see that CPU usage is really hovering at around 90% here, right? So this workload is really CPU bound. And then if you look at kind of the Grafana chart, you see CPU is your bottleneck. And so, of course, we need to figure out in normal troubleshooting what are the queries or statements consuming, who's consuming this highest CPU. But in production, you might not have the time to do that. And with the elasticity of the cloud, I check my current service objective, and this is 8 cores. I just want to mitigate the issue while I figure out the root cause. And so the first step is to just change my service tier objective to 16 cores. And what this does effectively, you'll see it's still 8, is this provisions a new compute, right? And once the compute is provisioned, then it'll do a failover to the new compute. And really this the whole provisioning takes about 60 seconds, maybe 60 to 90 seconds, but the failover should take no longer than 10 seconds. And so if we look at a connection resiliency, this is still an 8 core, so it's still in the process of provisioning, but my workload really is still ongoing. So there's no downtime during this point of time. The workload is still going, and it's almost pegged at 100%. So switching to this, you'll see kind of my code, the resilient connection code, which has caught a transient error, and then it's waiting for 5 seconds and will retry again, right? And so if you have transient fault handling logic, you won't even really realize, this outage, right? So let's take this area and zoom into it, and we'll see that the last connection was really made at 4811, or rather 4811 or 4812 actually, and the next one was made at 4827. That's roughly, and they are a second apart, so that's roughly 13 or 14 seconds of downtime, and there are times it's 6 seconds or 7 seconds, so it's between 6 and 12 seconds or so of downtime, which if you have transient fault handling or retry logic, your application won't even necessarily notice. Now if I look at service objectives, we have gone from what was an 8 core to now a 16 V core, right? And then looking at resource stats, you will see that instead of the 95% CPU, we are closer to a 50% CPU. Of course, we doubled our cores, right? We do want to, I'm not saying we shouldn't troubleshoot. We should troubleshoot, and see what was the top query in question. And you'll see the top query of question has a specific plan, and you can tune that. But always mitigating is an option due to the fast, scale up abilities in Hyperscale, versus actually trying to identify on the fly and fix on the fly, mitigate the issue, then figure out, how to bring down utilization by tuning queries and, getting back to the original, service tier. So this demonstrates, the fast scale up abilities of Hyperscale. As you can see, after we went to the 16 core, our CPU is really half of what it was, and the workload runs smoothly. You have breathing room, and if in fact you had more workload, you would be able to get better throughput for that workload due to the increased resources. We do have transient fault handling and retry logic now built into the drivers from ADO.NET perspective, and so you could have a config file that actually controls some of the things. Some of the retry logic options include the number of retries, the number of the errors that you consider to be transient errors, interval time, delta time, so on and so forth. And exposing them via config files means you don't need a code change to change some of those parameters.
Thanks, Denzel. As Denzel mentioned, my name is Balmukund, and I also work as a product manager with Azure SQL database team. Let's go over what's new in Azure SQL DB Hyperscale. We will talk about the feature which were released in the past under preview and were GA'd, and we will also look at the roadmap. First, let's talk about GODR and failover group feature. GODR is a technology by which we can replicate a single database across the region. It can be within the region as well, but it defeats the purpose of disaster recovery. So in GODR, we will replicate a database from one region to another. And as you can see in the picture, we have shown failover group at the same time. Thing to keep in mind is that in both the technologies, the failover group and GODR, the database is replicated asynchronously between the region. As you can see, each region will have its own set of page server and the log service. The failover group allows you to group multiple databases together, so they will fail over as a unit altogether. Failover group also provides us the endpoint, which are called as read-write listener or read-only listener. The advantages of these endpoints are that the endpoint will not change even if a failover happens of a group. The purpose of GODR is to do a planned or unplanned failover. The planned failover is typically done when you have to do a DR drill and test whether everything will work fine when there's a real disaster and you have to perform a failover of a databases or set of databases. And when there is a real disaster, when the one of the region goes down, in that case, you can perform a failover manually to other region so that the business will run as usual. This feature has gone GA in around month of June. Next is named replica. As Denzil mentioned earlier, named replica provides us a endpoint to connect to a database so that we can have application which are connecting to a named replica for read-only purposes. In this section, if you see, those are the named replicas which are of different sizes. Just to give a brief about the named replica, they are the databases which are read-only. You can give any name which you want. You can give a different name to the database. You can give different name to the logical server, by which it gives you capability to have application which can connect to those endpoint separately. You can have different sizes of the named replicas. As you can see in the picture, we are showing small, medium, and big size of named replicas. Since they share the same set of storage, which is the page server, log service, and the data file, they must be within the same region as the primary compute. If you see here, the primary compute is here. These are the HA replicas, which could be from 0 to 4, and you can have up to 30 named replicas in the same region. Since they are different endpoint, you can configure application to use a different login. You can have different set of rules defined because they are like a different databases. And as I said, you can have up to 30 named replicas, and you can scale up or scale down named replica based on the need of the application. If you compare that with HA replicas will be of same size as the primary compute, but the name replica can be of different sizes. The way you create name replica is either by T-SQL or by portal or any other possible means to create any replica. Let's move on to the next slide. If you want to monitor the geo-replication link, the latency, how much is there between the two databases which are part of geo-replication, you can use the DMV, which is sysdm geo-replication link status. I will cover that into a demo. And there's a new DMV which got introduced, has additional information now, which is called as DM database replica states. This DMV can be used to find out various replicas, including named replicas, HA replicas, and geo replicas, and what their current state is. This was the enhancement made based on customer request. Let's look at the named replicas and geo replicas and HA replica in action. Let's go to portal and have a quick look at the configuration of Hyperscale. Here I am in the portal. Let me go to the logical server. And on this logical server, I have various databases. Let's focus on Warehouse DB. And if I look at the replicas tab, there are various replicas available for this database. First is the HA replica. I have two HA replicas configured for Warehouse DB on primary. I have one geo replica which is on logical server called DPS 2022-SQL Server-DR, that is in a different region which is East US 2. And then I have created two named replica, one on the same logical server and other one which is called as underscore NR2 on a different logical server but in the same region. And as you can see that I have 6 vCore, 8 vCore against 8 vCore of primary. Let's look at the same information using the DMVs. First, let's have a look at the geo replica. If I execute this query, you would notice the current server is 2022 SQL Server and the partner, which is the DR server, is -dr over here. And the lag right now is 0 second. This is the second DMV, which is the DM database replica states. And if I run this DMV, I will see 6 rows over here. One is local and primary is the current server where I ran the query, and rest all are HA replicas, named replicas, and geo replica. If you recall, these two have the same replica ID, which means they are the HA replicas, and two are named replicas, and one is geo replica. And as of now, secondary lag seconds is 0. Now let's look at the failover group which I created, and let's perform a failover. If I go back to the logical server and look at the failover groups, this is the group which I created. And if you look at the databases, I have two databases in this group, Warehouse DB and DPS 2022 HSDB. This is the endpoint for read-write listener, and this is the endpoint for read-only listener. I can perform a failover using this button. But before I perform the failover, let's run the query and connect to various replicas and see the output. Here I am in the PowerShell, and I have already made a script which can connect to all the replicas together and run a query to get the server name and the database name. If I run the query, you would notice that I have made the connection to all the possible replicas, including HA replica. This is the primary compute, which is the read write, and you would notice that this is the DR, which is a read-only with the same database name. This is the name replica which I created, and this nodes is just what the text which I added. It is not the output of any DMV. Name replica 1 read-only, name replica 2 read-only. I connected to HA replica as well with the same database name by providing the parameter called application intent is read-only. And then I have used the read-write endpoint of failover group to connect, which is going to read-write updatability. And then I also use the read-only endpoint to connect to the read-only copy. And as you can see, this went to the DR side and this went to the primary. And let's go back and perform a failover and say yes to the warning. It will take a few seconds to perform the failover. And once the failover is performed, you should see the role getting switched. The portal will refresh in few seconds automatically. And as you can see, the failover just succeeded and the role got changed. DR became primary and the East US logical server became secondary. The endpoint remains the same. This concludes the demo. And let's go back to the next slide. Other thing which became GA roughly in March of this year, March 2022, is the maintenance windows. The maintenance window is basically flexibility given to a customer to define when it is okay for us to patch the database. Now, as you can imagine, software needs upgrade. It could be a OS, it could be a host machine which is hosting the guest machines, or it could be a SQL Server binaries itself. They all need patching on the regular basis. To make it easier and more predictable, we have given feature called as maintenance windows, which are called as a fixed maintenance window. There are 3 windows out of which you can choose when we should patch your database. It could be a default, which is between 5 p.m. to 8 a.m. That's the time zone of the region in which your database is deployed. You can also opt in to choose a weekday maintenance window, which is from 10 p.m. to 6 a.m. Monday to Thursday, or you can opt in for a weekend maintenance window, which is for Friday to Sunday, 10 p.m. to 6 a.m. local time of the data center. You can also configure to get alerts if there is a maintenance being performed on the database so that you are ready and you're aware of a downtime which might occur for a few seconds, but you know it is happening because of the maintenance activity which is happening. It is the same thing available in other tier as well. It is important to note here is that in hyperscale, the compute layer is the only layer which is inside the maintenance window. And as you can imagine, because of the resiliency in other layers, we do take care of having no downtime when we apply the patches on other components of the hyperscale. Let's talk about zone resiliency. It is also called as multi-AZ. Multi-AZ is a feature which allows you to create an hyperscale database where the components of the hyperscale, the separate layers of hyperscale, are in different zones altogether. This provides you the resiliency of the hyperscale database. By default, log replicas are having multiple copies. By default, page server also has multiple copies, which means if you want to enable the multi-AZ for a hyperscale database, all you need is a extra HA replicas, which will provide us resiliency, and we will deploy HA replica into a different zone altogether. So as you can see in the picture, there are three zones which we are showing here. If you create an HA replica, the compute has two nodes now sitting in a different zone altogether. So in case zone has to go down because of some unknown reason, we would do a failover of the compute to a HA replica so that it provides you high availability. Log replica are already inbuilt with multiple copies, so there's no action needed from a customer perspective. And even page server also has a set, which means there are two replica for each page server, as Denzil explained in architecture of the hyperscale. Once now the data files and the backup are same storage type in Azure. So you have to choose either a ZRS, which is zone resilient storage, or a RAGRS, which is a zone plus geo redundant storage. These two are the choice of storage in between you have to make so that your database, your hyperscale database is zone resilient. Now, RAGRS is required if you need a capability to do a geo restore of a database. Otherwise, you are pretty much okay by using ZRS or zone redundant storage as well. There are a few more features which are in public preview. As I mentioned earlier, we will cover both. So there are a few features which are in public preview as of now. One of them is short-term retention. As you can imagine, there are requirements from customer who wants to retain their backup, which is called a short-term backup, which are used for point-in-time restore. Earlier, they were allowed to keep from 1 to 7 days. Now you can increase that up to 35 days, which means you can restore a hyperscale database any point of time in last 35 days. This feature will be announced in May. So, and the backup billing was also introduced at the same time, which means any database which were created on or before, there's no backup billing for those databases. And we have sent advanced notification to customer when we were introducing this backup billing. One other thing which customer asked us very frequently is if we migrate a database from a BC or business critical tier or a general purpose tier to hyperscale, is there any option for us to come back from hyperscale because of some reason? And the feature which is there, it is called as reverse migration. It is typically a movement of a data between two different architecture altogether. You can imagine that you are having a database which is in business critical tier, having a different architecture. When you perform the migration or conversion of this database tier from business critical or general purpose to hyperscale, we have to create a new set of page server. So it is a size of data operation. It should not be treated as a SLO change, like for the cost saving purpose, which you typically might have been doing by moving a data from between GP to BC and back and forth. It is a way to reverse migrate a database from hyperscale tier to the general purpose tier. And as I said, it is a size of data operation because we have to make a whole movement of the data from one architecture to a different architecture. Now, this is allowed only for the databases which were moved prior to hyperscale tier. It essentially means that if you create a database brand new on hyperscale tier, you will not be allowed to move it back to the other tiers of Azure SQL database. And as you can imagine, the maximum size limit of other tiers, which is BC and GP, is 4 terabytes. So if you migrate a database from these tier to hyperscale, you can come back to general purpose tier only up to the time when it is below 4 terabyte, which is the max limit of the general purpose tier. And I think there's a time limit of 45 days in which you can come back to the tier other than hyperscale if you have done the migration. And next is long-term retention. Long-term retention is essentially is a capability which allows you to keep the backup of the database for a longer period of time, typically for the compliance purposes. In other tiers, you can keep the database backups up to 10 years based on the retention what you provide. You can have a monthly retention or weekly or yearly retention. That feature is there in Hyperscale now. With this, I will hand it over back to Denzil, where he will talk about serverless, which is also a preview feature. Over to you, Denzil.
So Balmukund has talked about some of the preview features. Also upcoming in preview is Hyperscale Serverless. And this enables fast and automatic compute scaling where CPU and memory auto scales dependent on the workload. So this allows price optimized memory management where we shrink and grow caches and we enable almost instantaneous CPU scaling. And then billing more importantly is based on compute used per second. So it's at the per second granularity and it's based on what is used by the workload. So on Hyperscale, the difference and serverless exists on general purpose, by the way. On Hyperscale, the difference is it's automatic storage scaling as well, up to 100 terabytes, because we have that separation of compute and storage. It is significantly higher I/O performance than general purpose tier because we have things like the local RBPX cache, so on and so forth. We have all the hyperscale goodies turned on. So you have read scale out, you have ability to configure HA replicas, and the serverless aspect can be configured either on your named replicas or on your primary or on your geo replicas. So it doesn't have to be all serverless or all provisioned, right? And like we said, it's fast restore speed for Hyperscale because all backups are based on snapshots. Right, so let's look at a demo now, and the demo will have kind of two parts. We'll look at scale out with named replicas, and on the named replica itself, we'll use serverless, and we'll compare it with provisioned. Okay. So I'm going to run a workload here, which runs. It's kind of like a sysbench version, if you will. Which is a popular benchmark, and I'm going to run it on both the primary and I have a named replica, and let's see the difference kind of in between the two. So to do this, I'm going to pull a Grafana dashboard, and the first thing we'll look at is the primary, and let's look at the last 5 minutes. And on the primary, you see the workload starting. A couple things we'll notice. This is your normal hyperscale. So this is Gen 5 16-week course provisioned, right? And we'll see pretty quickly that we hit about the 15,000 batch requests per second. So if we look at kind of the output of the workload, we see pretty quickly that that we are at the 17K batch requests per second with a latency of about 193 milliseconds at the P95. And then to look at the named replica really, on the named replica, we'll see pretty quickly we are building up to the same thing. It didn't start at 17,000, it started at 15,624, and pretty quickly we got to almost the 17,000, mark. Let's look at usage. So as you remember, serverless, we will actually bill, per minute. So let's look at the usage. And we see 15,000 here at the provision layer. This is the HS Gen 5 16. And at the serverless perspective, let's look at the last 5 minutes. And we should see a very similar profile, which is just over 15,000 batch requests per second on serverless. And you see this service objective is HS underscore S Gen 5 16. So it almost instantly scaled up from kind of your not being charged for anything to the max being 16, right? So scale factor is from 2 cores to 16 cores, because serverless does the slowest or the service objective is tied to a min and a max, and so you see the ramp up is pretty quick, and within a few minutes we achieve kind of parity with provision. So it's almost instantaneous scale. The other aspect of serverless we'll see if I zoom out. Actually, let's look at the metrics one more time. We are at around the same mark here. We are at 18,000 or 70,800 with a 167 millisecond latency. Similarly, almost the same here. We are at the 17,000 to 18,000 mark with a 161 or 179 millisecond P95 latency. So really, performance is no difference between serverless and not in this case. What I will show you, which is kind of a little different, is I'm going to zoom out to the last 12 hours. Right, and actually let's just zoom into this time frame, and we'll see that really there was a part of the workload that ran for a while, right, and consumed a lot of resources, in this time frame, and then really the server was dead, or the workload actually wasn't busy at all, and then it picked up again. And as you see, I mean, the time to pick up or drop off resources was pretty quick. Right? For CPU, it is pretty quick. For memory, it's a little, we do reclaim memory and shrink all our caches. It's not as instantaneous as CPU, but then there isn't significant delay either. So if you look at total server memory, which is our measure of how fast we can shrink the cache, the workload kicked up. It was almost an instantaneous growth of your buffer pool, which we'll see separately. And then as the workload died down, we started shrinking the caches, and you see the step equation where it drops to the minimum available. And similarly, when the workload picks up, it goes up again. For those that are familiar with SQL, memory clerks, if you will, I think I shrunk down to the wrong location. Okay. If you're familiar with memory clerks, if you will see that the buffer pool, which is the main, memory clerk here, was the one that actually shrunk and grew as your workload shrunk and grew, right? So that's one aspect of this. The other aspect is really, so how does billing look in this case? And here I have added a app CPU build, for the named replica. And let's refresh this. And the new billing is not yet come in. It'll take another minute, to show up. But you can see the database was pretty dead for most part, here. And then the workload required resources, so you were billed for the resources used. And as the workload died down, pretty much your billing goes to, the minimum level. As the workload kicks up, again, your billing, goes up. So this is per second billing based on compute resources. So again, this is the serverless usage-based billing type scenario. The other thing I wanted to point out is this, is doing a ton of query of 17,000 batch requests per second. So how does latency of I/O actually look, right? And so I've flipped to this, storage dashboard, which is nothing but virtual file stats differences, right? And these are your data files and sys.database files. And we'll see that if you look at latency really, I mean, this is kind of the 2 millisecond mark, right? So most of the files are in this, even remote IOs, these are all remote IOs, right? And the 2 millisecond file. There's one which is in the 3 or 4 milliseconds range, but that's kind of the remote IOs to, the paid servers. If we look at, the RBPX itself, which is the local IOs, that's the intelligent cache that we have, which caches your hottest pages that don't fit in memory. I mean, we're talking less than 1.25 milliseconds for that data access, right? And so that's just this. But we are doing also 14 MB per file across many files. So, cumulative IOPS right here across all the remote reads, we are doing 30,000, remote reads, right? So this is 29.5 thousand remote reads against, remote files. And so 176 MB per second being read at, 30,000 or 25.9 thousand, IOPS. So the latency, even for remote reads, is not like it's poor. The local cache is, of course, faster, given it is, local SSD as compared to kind of going over the network to a remote storage, which are the paid servers.
Thanks, Denzel, for the wonderful demo about auto scaling of serverless using the name replicas. Let's move on to the next topic, which is troubleshooting hyperscale. First thing you should know is that there is a service which is called as log throttling service, which runs on a compute node. You might wonder why there's a throttling service which is running on the compute node, and what is the purpose of it. As you can imagine, that log service is the only layer which is responsible to distribute the log records to the other components in the hyperscale tier. Now, it is possible that because of some reason in this whole distributed system, if one of the component is not able to redo the log record, it is going to fall behind. And if it is falling behind a lot, it may not be able to catch up in future as well. So that is the reason there is a log throttling which we do on the log generation rate on primary compute, so that other actors are not lagging behind and they get a chance to catch up. Now, as you can imagine, this is to make sure that the system is stable. There's no component which is falling too far behind so that it can never catch up. What essentially it does is it gets the log apply progress from the log service from the compute node, and it returns the last log block which got applied to either the page server or the name replica or geo replica. And if there's a actor which is falling too much behind, then we start throttling the log generation on the primary compute. As you already know, that the 100 Mbps is the limit, irrespective of the number of vCore which you choose in hyperscale tier, which is unlike other tiers. And once we identify, or this service identifies the actor which is falling behind, based on how much behind it is and the history of its catch up, we will start to throttle the log generation rate on primary. If there is a actor which is less than 1 GB, 1 gig behind, we don't take any action because we expect that it is pretty normal to have an actor behind by 1 GB and it can catch up. But if it goes beyond one GB, in that case, we start throttling the log generation on the primary. It will not cause any read performance issue on the primary or other tier. It will just the log generating components, which is like writing of the database, will be little slowing down because of log throttling. Now, when you start seeing the throttling, you will start observing the weight which is happening on the sysdm exec request or other wait stat DMVs. There's a hyperlink mentioned in the slide, which can be used for further diagnostics. But in general, you will start seeing various component based on whether it is a page server, whether it is a geo replica, whether it is a Xlog, whichever component is causing the log generation to throttle, we will indicate that into the weights. Only controllable weight, which is RBIO RG replica, which means there's one replica which is falling a lot behind, which is causing the log service on the primary to throttle the log generation rate. Uh, what can be done from the user perspective is basically remove the replica and add a new replica. And as you know, all the replicas are just the compute nodes. They read the data from the same page server. So spinning a new compute node is pretty much instant activity. It takes 60 to 90 seconds of time to create a new component. And now, since this is a distributed architecture and there are various components which are added, we have enhanced DMVs to identify what are the various components which are doing I/O. If you look at the slide, we are accounting the I/O which is done via on the file in DMIO virtual file stats. I have given hyperlink for all DMVs. You can also look at the resource usage for each component like IO or CPU in the DMV, which is DMDB resource stats. And then you can also look at the history of the workload group in using the DMV. We also have added the page server related IO counters into column in the various DMVs like query store runtime stats and DM exec request. If you look at the query plan in the picture, you can also identify how much read is done from the page server when a particular query was executed from the query plan. Now let's jump onto the demo and look at few troubleshooting which you could do in Hyperscale. Now I'm connected to one of my Hyperscale database. Let's run the query to confirm it is a Hyperscale database. And as you can see, the server name on which I'm connected is DPS 2022 server, which is what we have been using into this demo. And the database is warehouse DB. DB ID is 7, just remember the number. And currently, the SLO is 8 vCore. HS Gen 5 8 is 8 vCore hyperscale database on Gen 5 hardware. If I look at the virtual file stats DMV and try to execute it, you would notice multiple rows, one per file for this database. And this database ID 7 has 21 files as of now. And of course, number 2 is the transaction log file. The file ID 0 and DB ID 0, which is shown here, is essentially the RBPX of the compute node for this database. Now, if you look at the size of this RBPX, it is this big number which you see here. And if I do a math and convert the bytes to gigabytes, it is coming to 125 gigs in size. Now you might wonder, how do I calculate 125 gigs? Why it is 125 gigs, not less, not more? If I do a simple math and do select 125 divided by 3, it comes to close to 41 gigs. And if you refer the documentation, for 8 vCore hyperscale database, you get roughly 41.5 GB of buffer pool. And if you remember the theory which we described earlier, RBPX is 3 times of the memory which is given. So that's why you are seeing 125 gigs of the RBPX, which is the non-covering cache on the compute node. This is other DMV which I mentioned earlier, which you can use to identify the resource usage. Thing to keep in mind that this column only shows RBPX IO, which I explained in the slide already. This DMV shows periodic values for various counters like CPU, data IO, and log write, and this is populated every 15 seconds. So every 15 seconds, you would see a row here, which will be kept in the system for some time. And I also mentioned that we added page server reads into the DMV. So if I look at this, you might see few page server reads values, non-zero values, which means there was data which was read from the page server. Now let's look at one of the query which I ran earlier in the system. And as you can see, there were two queries which I ran, which were supposed to do a lot of I/O, it to read a lot of data. And if I look at the query store, let's pick up plan ID 1825. If I look at plan ID 1825, you would see that there were read from the page server which were done, which is already visible into the query store runtime stats DMV as well. Using this, you can identify various I/O which was being done from the page server. And this is one of the query which I ran. And if I look at the properties of this and look at the I/O statistics, you would start seeing new values, which is the page server read, ahead read and page server reads. Currently, they are 0 because I ran this query earlier as well, and the data got cached into RBPEX, so there's no read required from the page server. And with this, I will again hand it over to Denzil to talk about the best practices which can be followed to get the better performance from the hyperscale. Denzil, over to you.
Let's go over some tips and best practices. Because Hyperscale has a large database size, we've seen an increase in kind of the number of data marts or even large databases where data loading actually tends to be important, right? There is a video, I've put the link, so I'm not going to demo that necessarily. But on SQLDB in particular, to maintain the SLA and to give you the recoverability, we do throttle log generation rate on Hyperscale. That log generation limit is 100 Mbps, so your ingest rate is 100 Mbps, right? You can't go over that as of today. So using that 100 Mbps wisely is critical to this, right? Then in addition to that, for large tables in particular, consider partitioning and incremental statistics. Partitioning makes maintainability very easy. Offloading and archiving of data and switching partitions is super easy because it's metadata operations that's not necessarily fully logged. Right? Incremental statistics makes update of statistics if you're loading just the latest partition, to be just that latest partition, right? The second aspect of it is consider compression. Even though we allow 100 terabytes, compression does squeeze more from your 100 Mbps log generation rate, right? So if you compress, we're using page level compression, and what would be potentially 100 Mbps would now be 50 Mbps because the compressed page is getting logged. All right. Then there's the trade-off of row store versus column store, but that's really not a data loading question. That is, the raw structure of the row depends on kind of the usage of the data, right? If it's an analytic workload doing more group by type queries and analytic type queries, column store may be well suited, in particular if you have a star schema, large fact table, so on and so forth. If you're still doing a fair amount of point lookups and or you're retrieving all columns, then rows 2 might be more appropriate. And it's not a choice of one versus another. You can have non-clustered indexes on top of columns 2, and you can have non-clustered columns 2 indexes on top of rows 2. So it's not necessarily a straight trade-off of one versus another, right? We have mix and match type scenarios. Then while loading data, things like batch size and tab lock depends on or changes depending on column store or row store. On row store on a heap, tab lock may be efficient. On column store, tab lock will serialize things. Similarly, batch size, you want a larger batch size on column store so that they land on compressed row groups versus row store, right? The other aspect of it is index build. Index builds offline is faster than online, resumable. Um, but then it is offline in nature, so it's fine for initial data loads or staging tables or things where you're loading the full table and you want the fastest index build, versus kind of the resumable online. It's an online operation. If you have a failure, it can be resumed and picked up from where it was, at the trade of it being a little slower and generating versions, so a little bit more of log, right? And then from your loading pipeline itself, I still see customers doing a lot of truncate and load. Re-architecting pipeline to do efficient incremental loads would be the way to go from an application perspective. So that's data loading best practices. Then we have options with Hyperscale that didn't exist before, or weren't as easy as before, which is scale up versus scale out, right? And you have to consider that when you think of your workload growing, right? Enable applications to be able to offload reads to readable secondaries or named replicas. And so, it can be a cost semantics too in terms of, what you choose for the secondaries with the mix of serverless and non-serverless and scale up and scale out. There are different profiles. So don't only consider the traditional scale up if I'm out of resources at 16 core that I go to 32 core. And then Dimitri, one of my peers, has a good SQL database tips. There is a wiki for that and a script to download which checks some of the common best practices, if you will. And then all your SQL tuning best practices still apply, right? Things like compatibility level and with all the improvements in intelligent QP that we keep on producing, and then query store to troubleshoot things, and tuning and plan analysis. All your known SQL best practices still apply. Hyperscale is not any different from that perspective. And next, we tackle the question of who's using hyperscale and load patterns. Really, we've seen a variety. SQL Server is a general purpose database, so you get a lot of use cases, right? So you can have customers building cloud-borne applications, which want the separation or disaggregation of computer and storage. In these cloud-borne applications, also you can see row store, you can see column store, more row store, sometimes column store if it's analytics. Some of them use graph, use JSON, and a lot of the constructs that we're using in SQL DB. The beauty of it is SQL Server is a multimodal database. You have row store, column store, you have graph, you have JSON, and there are a bunch of developer improvements which are coming in, into various stages of previews and GA. And then there are workload patterns require independent scaling of compute and storage. That's the strength, right? So you don't have to tie storage with compute, and they can grow separately. Then compute scaling, like we talked about in the previous slide, scaling up versus out. You have patterns like API, the read aspect of scaling, serving a read API, and your read and write workload or write workload primarily goes to primary. Lots of customers, ISVs, using that pattern. You have IoT type applications where data is coming, ingested data is coming from either sensors or IoT devices or windmills, so on and so forth, and they require independent read and write scaling. There are ISV applications which are being modernized to use more SaaS. So ISV applications, there are a bunch of them who were traditionally on SQL Server moving to Hyperscale. Then there are large server databases migrating from on-premise because they want to give up data centers or move to the cloud. And like the elasticity of Hyperscale, which allows you to scale up, down fast, scale out, rather quickly. And then there are SMP data warehouses. I'm not saying it's the big MPP data warehouses. SMP data warehouses or data marts, where hyperscale is plenty enough, for the use case. And then we have a ton of customer stories if you look across the board, from IoT with Schneider to gaming with HiRes to banking with Clearant to, arts and music with BMI. And all these case studies really are on the Microsoft, website. We have cloud providers like Big Red Cloud and analytics and more of predictions with ClearSale. And then we have ISVs like Quest Analytics and Avnet as well, adopting hyperscale. So, needless to say, we see hyperscale as the future. It's not only for big databases or small databases, it's for any databases. It harnesses the power of SQL Server and lets you that elasticity that only hyperscale can give you. Special thanks to all the sponsors supporting this conference. And please, there are ways to win prizes. As the slide says, post your selfie. And please enter session feedback and conference feedback so that we can improve and tailor our sessions to make them useful to you. Thank you for your time. Please, we would be, during this time, we'd be happy to answer any questions. So feel free to post them, and we'll try to get them answered as best as possible.